It's like the
是一份6页的educational policy explainer， 就是你解释一个高等教育的政策，非常简单。我发给你啊。
还没看。那你觉得怎么样？这种课程？你跟单位发的学校要做什么确定没啊？我应该确定。
你因为
就那60小时可以不用钱还。
你好。
这很容易，问一下。夏天才有时间做，秋天跟春天还蛮多在休息的时间。
但是我看到我倒是可以多少求一点。
你夏天可以做，那你夏天干嘛？
夏天最多能学，就是能挑出一门有价值课的好不容易。我问了一下。
我觉得经济学系，应用经济学系的美术班，你那个刘老师很好。
那是我肯定不会学的美术的那个。
是我那个台湾朋友的教授。
但是我觉得我用不上美术的那个。
用不上，教育政策里面。那个高考资本是什么学校？那个不用美术班。
我看一下，我反正最多学，我最多学一门课，不是。我觉得这个我没有这个风险大，因为我没一点大自己的，我也不晓得什么是他这门课教什么，然后我们可能对，就算他告诉我一点名词也不知道，他告诉我他说我们要学哪些，我也不晓得讲这个内容到底是什么，然后具体在哪个方面应用，是一抹黑啊，风险很大。
哎，这次作业不行哦。就是这个。
All right. Should we start?
他是没怎么改。
So today I'll make some announcements and review the last 2 lectures, which won't be about the midterm 2, but it'll be coming up the final. So, and then I'll do some standard practices with RDD, and actually there are some flashcards for the midterm 2. I made a small change actually. There was a typo here. So it used to be GLS, but it's really WLS. I made a small change in that flashcard, so you don't confused about it. And any questions about the midterm 2? Nope. Make sure. Oh, sorry.
I was just wondering, I'm a little confused about how much IB is going to be on the exam.
Okay. Yeah.
Because like there was a time where you said like stop studying here, and then there was another time in review when you said
So,
IB is not on the exam.
in the official terms or whatever, it's supposed to be on the midterm 2, but there is no question about that.
Okay.
About the late and Kate and IB and stuff like that. Things we'll cover or review in the section today. All that stuff won't be there in the midterm 2.
So the entire IB lecture.
The IB lecture will be there up until the late part.
Okay.
Yeah. Good. Yeah.
We need to use a calculator, but I'm just wonder how much do we need to calculate during the exam?
Not so much. As long as the calculator has an explanation feature in it, that will be fine. And you don't have a lot of stuff to calculate. That's what I can say. Or an app that, or calculator app that has a explanation feature in it. Good.
Okay.
Yep.
So the IB section will stop until slide 49, or
Oh, what?
cover the content approach? Will this cover?
Yeah. Effect heterogeneity in IB, all of that stuff is not the it's not gonna be there in the midterm 2. Good. Any questions?
就是看一下这个 slides，
Nope.
还有看一下那个，
All right.
看一下
Should we start?
set。对，就是它这个 flashcard，
Any questions?
重点看一下这个 slide。
Anyone? Is there anything to discuss? No? All right.
Oh, sorry, I wasn't sure. So I know that like for the random intercepts, random slopes model, you're talking about like, I know the Winship model uses set rotation, there's use like a different rotation. Do you think for our purposes, do you think it's necessary just to kind of get the basic ideas of random intercepts models and random slopes? Or should we like jot down specific rotation?
I would recommend jotting down some specific notations because it's really helpful. But there is no question about like there is this model. You should basically put it into a mathematical notation and like a regression equation out of the state output or something like that. There's no question about that in the midterm too. I cannot guarantee you that in the final, but there's no question about it. That's yeah. Any other questions? Nope. All right. So again, all of the stuff that we're going to cover here today will be in the midterm too. All right. But it'll come up in the final, so it is. So I hope it's helpful. So we covered effect heterogeneity and ID, right? So it starts with this situation. This is the DAG that you have typically utilized as ID, right? But the problem here is that the path coefficients are different across units, right? So in this situation, if you use IB, this is covariance between Z and Y divided by covariance between Z and T, right? That would be expected value of AI BI divided by expected value of AI. So it'll be just like Rice path. It is an application of Rice path, but you are multiplying A and B specifically to the ith observation. Specifically for the ith observation, right? And then you do that, you multiply A and B for the ith observation, for the first observation, second observation, third observation, etc., and then you are averaging them out. That's the expected value of AI, BI. Does that make sense so far? Good. And then covariance between Z and T here is expected value of AI. Good. All right. And if you have covered it or remember it from 361, it should be expected value of A1, expected value of BI, sorry. Covariance between AI and BI. Divided by expected value of AI. That is the rule, basically. If you are interested in learning how that works and stuff, I can demonstrate that in my office hours, but you can simply accept that as a rule now, for now. Good. Any questions so far? Nope. All right, good. So, what does that mean? If there were no heterogeneity in effects, then it could have been AB, right? Expected value of AI would be A, right? And expected value of B would be B. But and there's no heterogeneity, so there's 0. But precisely because there's covariance between AI and BI, the IV estimator does not identify the ATE if there's heterogeneity and covariance between the AI and BI. Do you want me to repeat that? Okay. The IV estimator right there does not identify ATE, the average treatment effect, if there's effect heterogeneity and there is covariance between AI and BI. This is the different part from the IV without effect heterogeneity, basically. Good. Any questions? Does it make sense? Because of this part is IV becomes different. Right? The average treatment effect is AB divided by A, right? It should be that, right? But there's this part, so that way it's different. Good. So instead, so we cannot really identify ATE now. Okay? So what we do here is to try to identify local average treatment effect instead. Instead of trying to identify the overall average treatment effect, we're trying to find the local one. So basically, we focus on the average treatment effect of a specific group of people. Good. Not the whole population. And we expect that the effect heterogeneity issue is resolved with that approach. As long as we focus on a specific group of people, the identification issue will go away. That's our hope. But obviously, it loses some generalizability, right? So the question is, what kind of people are we talking about, right? What is this specific group of people? And that's why we learn compliance classes. The first one is compliers. So subgroup, this is subgroup, S means subgroup, is compliers, C, if treatment TI1 is 1 and TI0 is 0. What does that mean? That was from the lecture slides, right? What does that mean? Yep.
If they get assigned treatment, they will get assigned treatment. Like
They will actually get the treatment, right?
right. And
Yeah.
if they aren't assigned the treatment, they will not get the treatment.
Yes, exactly. That's the compliers, right? So PI of one here means that they are assigned to the treatment group. And the actual treatment outcome is 1. The actual treatment is 1. And if they are not assigned to the treatment group, they won't get the treatment. And what about defiers? It's exactly the opposite, right? Right. So if they are assigned to the treatment group, they won't get the treatment. And if they were assigned to the control group, they will get the treatment. Okay. This class is really hard to find in our real research, actually, right? It's kind of hard to understand why would they defy in this situation, right? In certain settings. So it is different from always takers or never takers, right? Always takers defies the assignment rule only if they got assigned to the control group. If they were assigned to the treatment group, they will just comply because they will always take the treatment. But they will defy to the assignment rule if they were assigned to the control group and get the treatment no matter what. Okay. And never takers never takes the treatment no matter what. Kind of like you got assigned with a lower number of draft lottery and somehow you're trying to get out of the military service as much as possible and then somehow don't get the treatment of military service after all. Good. Any questions with that? Or note that this is all latent classes. Why is that? It really think about the two situations one person can be in, right? There's got to be a factual situation and counterfactual situation because you cannot be in both situations, right, at the same time, right? So that's why it's they're all latent. You cannot pinpoint somebody and say, oh, you're a compiler or you're a never taker. Any questions? All right. Sure.
So just that compliance class is only for binary treatment.
Oh.
Right.
Yeah.
Okay,
Yeah.
So that,
Mm-hmm.
and if the IV is not binary, rather than binary, if IV is like continuous,
Mm-hmm.
how do we define
But
classes?
oh no, this is the binary case actually. So the compliers can be defined in the continuous cases. It's too difficult to do that in our class because it requires a lot of math. But
There is
it is doable. Yes. Yeah. But for the sake of convenience, we just focus on binary cases. Any other questions? Nope. All right. So what we're doing here is basically we're trying to identify compliers ATE via IV. Kate. So all of these four compliance classes, we're trying to identify the causal effect for compliers only. Okay. And IV can be a strategy to do that. Kate is defined as BC, the beta coefficient or the causal effect of B for the compliance groups. For the complier groups. Okay? That's why it's BC. Okay? And it's defined as expected value of BI's given subgroup is C. So this is the individual treatment effects average, which means average treatment effect, right? This is still average treatment effect, but just for compliers. Does that make sense? Yeah. All right. And IV will estimate it by expected value of Y given Z is 1, S is C. And expected value of Y given C is 0 and S is C. What does that mean? What is going on here? What is going on? What does that try to achieve? So this part is expected value of Y for those who got assigned, right? Z is 1, right? And the expected value and minus expected value of Y for those Z is 0. So you're looking at as Z changes, how much of expected value of Y changes, which is, yep.
Is it the naive estimator?
Sort of like covariance between Z and Y. That's what it's looking at. So this is the covariance between Z and Y, but for the compliers only. Good. Any questions? And now here is Z by T, sorry. The notations are same except that Y is P here. It's the same thing, right? Covariance between Z and T here, but for compliers only. Right? Any questions so far? And how one does obtain this number? That is the question, right? So let's make an assumption and a DAG. So the assumption right here is that there's no defiers. Okay. This is called monotonicity. Monotonicity, which is hard to pronounce. That assumption, basically. There's no defiers. That's the assumption right there. Having said that, let's look at the DAGs of always or never takers. Okay. Yep. Oh. You know, it's U T Y Z right there. And oh, there's no arrow actually. AI, comma, AN, and BI, comma, AN. It means that the path coefficient of BI for those who are either always or never takers. Okay. And AI means the path coefficient between the two variables from Z to T for those who are always or never takers. There's no path right there. Why is that? Which means it's 0, right? This part is 0, right? Why is that?
Because the assignment doesn't affect the treatment status.
Yes. So regardless of whether this person got actually assigned, this person got assigned to the treatment group or control group, always takers will get the treatment no matter what. Right. So let's look at this DAG. Why is the relationship between Z and T is 1? The path coefficient between from Z to T is 1. Why is that? Yeah.
Is it because, so like with the incident, because it directly causes the treatment, it would be, if it's like a 0-1 variable, if it's 1 treatment, you multiply by 1, the treatment will be 1. But if you don't get assigned treatment, it'll be 0, you multiply by 0, the treatment will be 0.
Right, so that's why it's 1. And notice that there's no path between U and T. Why is that? Because there's, precisely because Z perfectly determines T, and T, there's no room for errors. Right? T only is decided by Z only. Good.